Okay, we'll get started. So let's settle in. So it seems as if a fair number of your classmates have decided to take an early spring break, but I thank you for your dedication in being here. So we do have some important things to cover. All right, so we're going to talk about today the last category of aqueous reactions that we're going to deal with in Chapter 6. These are called redox reactions. Last time we introduced precipitation reactions, which is where ionic compounds exchange their ions with each other, and in some cases you get an insoluble precipitate forming. And we also talked about acid-base reactions, which is a similar concept where instead of ions being transferred, you have protons transferred with recombination of H plus and OH minus. So we have those two classes of reactions, and we have a last one here that we're going to talk about. In this case, the products of these reactions are not as predictable. So we're not just going to expect you to be able to come up with what the outcomes of these reactions are, but we do have to learn some features of them and how to balance these reactions, which is sometimes more challenging than what we've seen before. Okay. All right, so to get started, let's talk about some of the key terminology associated with redox reactions. So redox reactions are reactions that involve transferring electrons between the reactants. So one reactant is going to lose some number of electrons. One of the other reactants is going to gain some number of electrons, and that's what we're talking about when we deal with redox reactions. Okay, thank you for stopping talking finally. All right, so we're going to talk about redox reactions. There's two things that always happen in a redox reaction. You have oxidation and reduction. That's where the name comes from. So oxidation is loss of electrons. Reduction is when something gains electrons. And the key point with redox reactions is that these two things have to happen together. You can't have one without the other. So if you have if you have an oxidation happening, you also have a reduction happening at the same time. And so because these things always come together, that's why we call it a redox reaction. And this is then a reaction that involves the transfer of electrons. All right, so there's a nice little mnemonic device to help us remember the difference between oxidation and reduction. So the mnemonic goes, Leo says grr. So Leo is a lion, and lions say grr. And so if you lose electrons, that's an oxidation. And then if you gain electrons, that's a reduction. All right, so that's how we remember which one's which. Leo says grr. All right, so in order to help us balance redox reactions and really to be able to classify what a redox reaction is, we have to know whether something is losing or gaining electrons. And sometimes it's not always obvious just by looking at the reactants and products whether a redox reaction actually occurred. So to be able to balance these reactions and to be able to classify them, we need to assign what are called oxidation numbers. So essentially what we're going to do for redox reactions, or really for any reaction we could do this, is assign the oxidation number of every atom that's involved in the reaction. And a redox reaction is going to involve two of those oxidation numbers changing between reactants and products. And that's how we know that it's a redox reaction. So we have to get good at assigning oxidation numbers. Oxidation numbers, in some sense, they have some similarity to formal charge, but they're defined a little bit differently. So we defined formal charge back in chapter, I guess it was 3 or 4, which relates to the charge that an atom would have in a covalent molecule if all of the electrons were shared equally. But here for oxidation number, the way we classify this one, it's just another way of counting electrons, another way of counting them. And it's the charge that an atom would have if the more electronegative atom got all of the electrons. So if you have two atoms bonded to each other, the oxidation number assumes that the more electronegative atom takes all of the electrons, and that's going to be its oxidation number, is whatever that charge represents, and then the other atom would have the corresponding charge. So it's defined differently. We don't need to worry about the precise definition, but what we do need to know how to do is how to assign oxidation numbers for any element in a compound. So there are some that are obvious. So just like we saw for solubility rules, we can start with the obvious ones, and then obviously some other ones that are a little bit trickier. So the first thing is that if you have an atom that's in a neutral element, either an atom by itself or if it's a diatomic like O2 or F2 or something like that, so it's just an element by itself, the oxidation number is 0. So we'll use ON to abbreviate oxidation number. And anytime you see an element by itself, it's going to have an oxidation number of 0. Another one that's fairly obvious is if you have an ion by itself. So if we're writing an aqueous reaction and you have some cation or anion by itself dissolved in solution, or if you have two ions paired together in an ionic compound, whatever the situation is, the oxidation number for the ion is just equal to its charge. So whatever its charge is the oxidation number. So we don't have to learn anything new here because we know how to assign the charges of ions in an ionic compound. And so the oxidation number would then just be the charge if it's just a single ion by itself. So a Na plus would have a +1 oxidation number, Cl minus would be -1, and so on. So those are pretty straightforward. Another important rule, which is going to then help us for assigning the rest of the oxidation numbers, is that the sum of the oxidation numbers has to equal the total charge. So we saw that we had a similar correlation with formal charges, and for oxidation numbers it's the same. You add up all the oxidation numbers in a polyatomic ion or in a molecule, and the sum has to be equal to the total charge. Alright, so we'll see examples of this, but if you have the NO3 minus anion, one that we've seen a lot, the sum of all the oxidation numbers for the nitrogen and the 3 oxygens has to equal to -1, which is the total charge. So that's always going to be true whether you're talking about neutral or charged species. And then taking it a little bit further, we talked already about ionic compounds. So if you have a metal in an ionic compound, this really follows from rule number 2, but it's a slightly more precise way of saying it. If you have a metal in an ionic compound, it's going to always have a positive oxidation number that is equal to its charge in that compound. Okay, so we have this situation. Anytime you have a metal in an ionic compound, just figure out what its charge is in that compound, and that's the oxidation number. For the nonmetals, it's a little bit trickier because some nonmetals have variable oxidation numbers. They don't always have the same oxidation number in every compound. But again, there are a few nonmetals that are more obvious and ones that we should focus in on first when we're assigning oxidation numbers. So hydrogen's a pretty easy one because hydrogen, if it's by itself in H2, it's going to be 0 like any other element. But if hydrogen is in a compound, forming covalent bonds, it'll have a +1 oxidation number when it's bonded to a nonmetal. So just about all the compounds we'll talk about with hydrogen have hydrogen bonded to a nonmetal. Things like water is a classic one. And in that situation, hydrogen would have a +1 oxidation number. Now there are a few rare examples where hydrogen has a -1 oxidation number, and that's when it's bonded to a metal or a metalloid. Remember that metalloids are things like boron and silicon, and a couple other examples that you might see. So we haven't seen a lot of examples like this, but there are compounds that involve hydrogen bonded to a metal. They're called hydrides, and in that case hydrogen has a -1 oxidation number. Well, you won't see those very often. And then the last 3 rules deal with other nonmetals that pretty much have invariant oxidation numbers. So fluorine, as I said in this case, where oxidation numbers refer to giving all of the electrons to the more electronegative atom. Fluorine is the most electronegative atom, so it's always going to pretty much have a -1 oxidation number when it's in a compound. Like I said, fluorine by itself, F2 would still be 0 because it's an element, but if it's bonded to something else, anything else, it's going to have a -1 oxidation number, so look for that one. Another one that's almost always true is oxygen, which is typically -2, except when it's bonded to itself or to fluorine. So oxygen is the second most electronegative atom, so in almost every case it's going to have a -2 oxidation number. It gets all of the electrons in that bond for the purposes of assigning oxidation number. And then finally, the other halogens, chlorine, bromine, iodine, those are going to be -1 pretty much in every case, except when they're the central atoms. We've seen that there's some compounds that have a halogen as a central atom, or if they're bonded to F, an oxygen, so something more or less negative. All right, but these are ones that we can sort of look at when we're assigning oxidation numbers, because as I said, a lot of elements have variable oxidation numbers. So we want to assign the obvious ones first and then use rule number 3, which is the sum of the oxidation numbers equaling the total charge, to then help us figure out the rest. So let's see some examples of this for just determining oxidation numbers. Determine the oxidation number of each element in sodium sulfide. So we know how to write formulas and charges for ionic compounds now. So sodium, let's find it on the periodic table, just remind ourselves how we do this. Sodium is Na, it's right there, atomic number 11. It's in group 1A, so it's always going to have a +1 charge when it's in an ionic compound. So we have sodium plus. Sodium plus is going to combine with sulfide. Sulfur is in group 6A. It gains 2 more electrons to get to a noble gas configuration. So sulfur, just like anything else in this column, would form a -2 anion. So Na plus combining with S2 minus. The formula for the neutral compound is Na2S. And as we said, for ionic compound, the oxidation number is just equal to the charge on the ion. So each sodium, there's 2 sodiums, each one is going to have a +1 charge, and it's going to have a +1 oxidation number. And then the sulfur that's in there has a -2 charge as sulfide, so its oxidation number is going to be -2. So those are the oxidation numbers for each element in that compound, and we can verify that, remember, the sum of the oxidation numbers equals the total charge. Sodium sulfide is a charge-balanced neutral ionic compound, so the sum of all the oxidation numbers should be 0. We have 2 sodiums, each with a +1 charge. We have 1 sulfur that has a -2 charge. We add those up and we get 0. So ionic compounds are pretty straightforward, especially when they just have monoatomic ions where you don't have polyatomics, just a single sulfur with a charge on it. The charge on the atom is equal to its oxidation number. We can look at a slightly more complicated example. So let's look at the oxidation number of each element in phosphoric acid. That's the one you guys have. I changed this one at the last minute, but I think it's phosphoric acid in your notes too. All right, so for phosphoric acid, we have, remember, the name comes from the name of the anion that makes it up, so we're doing some review here on acid nomenclature as well. Phosphate is PO4 3-, which means phosphoric acid is H3PO4. All right, so when we have a compound like this, we can first assign the obvious oxidation numbers first. In any acid, like phosphoric acid, hydrogen is bonded to a nonmetal. It's going to actually bond into one of the oxygen atoms. But anytime you have hydrogen in a covalent compound, remember that the oxidation number for hydrogen is always +1 when it's in a covalent compound. And then oxygen, same story. If it's in a covalent compound, unless it's with other oxygens or with fluorine, remember that PO4 3-, there's no oxygen-oxygen bonds. All the oxygens are bonded to the central atom. So in this case, all the oxygens are bonded to phosphorus, so they're going to all have a -2 oxidation number. So that's another fairly obvious one to look for, is oxygen. And then finally, we have to assign the oxidation number for phosphorus, and this is one that can be variable, so we have to use the fact that the sum of the oxidation numbers equals the overall charge. The overall charge for phosphoric acid is 0, and so if we add up all the oxidation numbers, we have to pick the correct oxidation number for phosphorus to make the overall sum equal to 0. So it's just a little bit of algebra here. The sum is going to be 0. We have 3 hydrogens, each with a +1 oxidation number. We have 4 oxygens, each with a -2. And then we have 1 phosphorus, which has its own oxidation number. And so the oxidation number for phosphorus is going to be equal to +5. We're just doing a little bit of algebra. So if we have a +5 oxidation number in phosphorus, the sum of all 3 of these will come out to 0. Remember, we have to account for the number of each atom there is. So there's 3 hydrogens, each is +1. 4 oxygens, each is -2. Add that to 1 phosphorus with a +5. You get a sum of 0. So our phosphorus is +5, and that's going to be then all of them in this compound. Okay, so things like nitrogen, phosphorus, carbon, those tend to have variable oxidation numbers, so you're going to assign those last. Start with things like hydrogen and oxygen and fluorine, which are pretty much invariant. And then finally, one last example where we actually have a charged species is the oxidation number of each element in the sulfate anion. So the only difference in this case is we're just giving you a single anion by itself. So the formula for sulfate, which we should be familiar with, is SO4 2-. And then again, we look for the obvious ones first. So we have oxygen and sulfur in here. Oxygen, because it's bonding to another nonmetal, is going to be -2. This is the structure of sulfate. There are no oxygen-oxygen bonds, remember. All right, so we have oxygen is -2, and then we have to find out what the oxidation number is on sulfur. And again, we're going to go back to that rule that the sum of the oxidation numbers has to equal the overall charge. Now, in this case, the only difference here is that sulfate has a total charge of -2. So we don't want to set this sum equal to 0. We want to set it equal to the actual charge, which is -2. There are 4 oxygens, each with a -2 charge. And then if we have 1 sulfur, what does its charge have to be such that the sum is equal to -2? That comes out to +6. All right, so if sulfur is +6, we have a +6, we have 4 -2s. The sum of those equals -2, which is the overall charge in the anion. So sulfur is +6. Another rule that's not really important, but is maybe a good one to keep in mind, is that the maximum oxidation number for an element is equal to its group number. So sulfur is in group 6, so +6 is the highest it could go. But it is a variable one, so it could be something other than +6. That's why you have to use this rule here to figure out what it actually is. But it'll never go higher than what its group number is, which for sulfur is 6. All right, so we're going to have to become really good at assigning oxidation numbers, because the next thing we're going to talk about is how to balance redox reactions and how the oxidation number plays into that. So the first thing we can do is bring in a couple more definitions. This is where things become even a little more confusing, because when we have a redox reaction, which is, again, transfer of electrons between the two reactants, one of the reactants is going to be classified as an oxidizing agent, and one is going to be classified as a reducing agent. And the definition is almost backwards. So the oxidizing agent is the reactant that gets reduced. So whichever species gets reduced in the redox reaction is what we call the oxidizing agent. It's going to be one of the reactants. We're only looking at the reactant side when we're classifying oxidizing and reducing agents. Now, the reason we call it the oxidizing agent, even though it's getting reduced, is because an agent is someone or something that does something. So the oxidizing agent is the thing that does the oxidizing. So that's why we call it the oxidizing agent, even though it's getting reduced. And then how do we identify this in a chemical reaction? So what we look at is the oxidation number and how it changes during the reaction. So for the oxidizing agent, the oxidation number will decrease. Okay, so we'll see a bunch of examples of this, but basically if the oxidation number goes from something higher to something lower during the course of the reaction, so we find the oxidation number on the product side, if it's lower than what it was on the reactant side, that means it's getting reduced, which means it's the oxidizing agent. The reducing agent is the exact opposite. It's the reactant that gets oxidized. My tablet wants to go on spring break early. Video recorder causes problems sometimes. Okay, so the reducing agent is the reactant that gets oxidized in a chemical reaction. Which means it's the reactant that's losing electrons. This is the species that does the reducing. then that means the oxidation number increases during the reaction. Now, a little bit of a note about this terminology. As we'll see when we do these, typically what happens is that the oxidation number for only one of the atoms changes, but we would classify the whole ion or the whole compound that atom is part of as the oxidizing agent or the reducing agent. So it's not just the atom itself that's the oxidizing or the reducing agent, it's the whole species that it's part of. We're always going to have one oxidizing agent and one reducing agent in a redox reaction, never more, never less. Okay, so we'll start seeing examples of that. So the first thing we're going to talk about then is just classifying, whether this is a redox reaction and what is the oxidizing agent. So how do we do that for this reaction here? We have 2 PCl3 plus O2 making 2 POCl3. So if we wanted to decide whether something is a redox reaction, we have to first assign oxidation numbers. We learned last time how to tell whether something is a precipitation reaction or an acid-base reaction. Now we have to learn how to classify redox reactions, and for that we just have to look at oxidation numbers, because it's not always obvious just by looking at the reaction, especially for redox reactions which have a number of different forms. All right, so let's assign all of the oxidation numbers for everything in here. So we have PCl3, so we're going to draw little lines and assign the oxidation number for each element, for each atom. Okay, so remember that chlorine, if it's the outer atom, it's going to be -1. It's the more electronegative atom in this case. Phosphorus is the central atom. If we have 3 -1s, then the central atom has to be +3 to balance the oxidation numbers to equal 0. So we'll start doing this a little bit faster now, but we'll have to just keep practicing this until we get good. So we have 3 -1s and a +3. O2 is an element by itself. So remember that any element by itself has an oxidation number of 0. So we don't have to think too hard about that one. And then finally in the product, POCl3, we have still the chlorines on the outside that are -1. Oxygen is now bonded to phosphorus, so it gets a -2 oxidation number in the product. And then if we have 3 -1s, 1 -2, what does phosphorus have to be to balance that? It has to be +5. So we have, this is the 3 oxidation numbers for the product POCl3. One thing to keep in mind is when we're assigning oxidation numbers, we ignore the coefficients. It doesn't matter that there's 2 PCl3 here. All that matters is that each phosphorus is +3, each chlorine is -1. There are 2 of those molecules, but that doesn't change how you assign the oxidation number. So we don't have to worry about the coefficients in the chemical reaction. We just have to worry about the formula of each reactant and product for assigning oxidation number. So if we look at what happens here, we see that we have some oxidation numbers changing. So phosphorus goes from +3 to +5. So on the reactant side, phosphorus has an oxidation number of +3. On the product side, it has an oxidation number of +5. So its oxidation number is increasing. And then for oxygen, we see that on the reactant side, it has an oxidation number of 0. Each oxygen is 0. And on the product side, the oxygen is -2. So because we have oxidation numbers that are changing between the reactant and the product, this is in fact a redox reaction. Okay, so choice A, is this a redox reaction? The answer is yes. And then now we have to assign the oxidizing agent. So remember that the oxidizing agent gets reduced. Which means the oxidation number decreases. All right. So O2, if we look at oxygen, the oxidation number starts at 0 and goes to -2. So between the reactant side and the product side, the oxidation number of oxygen is decreasing. That makes O2 the oxidizing agent. Remember, it's the entire species that it belongs to. All right. So that's how we assign oxidizing and reducing agents. We have to put the oxidation numbers for each species in the chemical reaction and find out which one's increasing or which one's decreasing. Okay, let's do one more example like this. where this time we'll take the product of that first reaction, POCl3, and then it reacts with water. This is called a hydrolysis reaction to make phosphoric acid and hydrochloric acid. Okay, so that's the second reaction we'll consider. We have to answer the same questions. Is it a redox reaction, and if so, what's the oxidizing agent? So we have to start by assigning all of the oxidation numbers to decide if it's a redox reaction or not. POCl3 is the same thing we had as the product of the previous reaction, and as we saw, the oxidation numbers were +5, -2, and -1. So we already did that one in the last problem, but again, chlorine is -1 when it's in a compound, almost always, if not the central atom. Oxygen is almost always -2 in compounds when it's not bonded to itself or fluorine. Phosphorus has to be +5 to balance out the oxidation numbers to equal 0. Next we have water. Water is one that we're going to see all the time in redox reactions. So let's get the hang of how this one works. And this is a very obvious one. So oxygen is -2 when it's in a compound. Hydrogen is +1. So if you see water, very quickly assign the oxidation numbers as +1, -2, and be done. Now if we look at the product side, we have H3PO4 and HCl. We did H3PO4 earlier also, and as we found, the oxidation numbers were +1 for hydrogen, it's hydrogen in a covalent compound, -2 for oxygen, oxygen in a covalent compound is -2, and that left +5 for phosphorus. So we did that one earlier as well. You have 3 +1s, 4 -2s, and then a +5 cancels it out to equal 0. And then for HCl, we have two nonmetals bonded to each other. Chlorine in a covalent compound is -1, hydrogen in a covalent compound is +1. Okay, so we're going to get the hang of assigning these eventually, and this is what we do for this one. Now, if we look at the oxidation numbers for everything that's involved here, we look at each element that's in this reaction. So phosphorus on the reactant side is +5, and it converts to a +5 on the product side. So phosphorus is not losing or gaining electrons. Oxygen on the reaction side is -2. We go to the product side, and it's also -2. Now there are two oxygens on the reactant side, but both of them are starting as -2, and all the oxygen on the product side is -2. So oxygen is not losing or gaining electrons. Its oxidation number is staying the same. Chlorine, same story. It's -1 on the reactant side, -1 on the product side, and then finally the last one is hydrogen. All instances of hydrogen on both the reactants and the product side are +1. So none of the oxidation numbers are changing here. Phosphorus, oxygen, chlorine, hydrogen all stay the same between the left and the right side of the reaction. So this is not a redox reaction. All right, like I said, it's sometimes not obvious just by looking at it whether it is or is not a redox reaction. But by assigning all the oxidation numbers, we can tell this is not a redox reaction. And because of this, we don't even have to answer question B because there is no oxidizing agent if it's not a redox reaction. This one is not a very obvious case, but this is an example of an acid-base reaction. So it's not the type of acid-base reaction that you're going to be expected to be familiar with, but it is also classified as that. Pretty much every chemical reaction is classified as precipitation, acid-base, or redox. This is clearly not a redox reaction. It's not a precipitation reaction because it doesn't involve ionic compounds, so really by default it's an acid-base reaction, even though it's not the most obvious one for the type that we talked about last time. All right, the last thing we're going to close off with before I set you free for spring break is how to balance redox reactions. Now, I think this is a lot of fun. You and I have very different definitions of what fun is, so maybe you won't think it's fun, but I do think it can be a challenging type of problem, but once you get the hang of it and once you practice it enough, I do think it's enjoyable and relaxing to do this. So we're going to learn how to balance redox reactions using the oxidation number approach. You're going to want to learn how to do it this way because these are the types of reactions that it's not going to be very easy to balance by inspection. We learned a few lectures ago how to balance chemical reactions, and for fairly simple ones we can just add coefficients, count up the atoms, and kind of guess and check ourselves and eventually get there. But these ones often have very involved coefficients, and you have to make sure that two things are true. One is that the number of atoms has to balance, and then also the charge has to balance. So if you have a net charge on the reactant side, you have to have the same charge on the product side. So there's a lot going on here, and just trying to randomly add coefficients for these is almost never going to work. So you definitely want to learn how to use the oxidation number approach to balance these, which is what I'm going to show you today. All right, so they can be quite difficult if you just try to do it by inspection. So the first thing we have to do when balancing a redox reaction is assign the oxidation numbers for each atom. All right, so assigning oxidation numbers is going to become quite important for us because we can't begin to balance a redox reaction without having the oxidation numbers for each atom well defined. Okay, so if we start with this set of reactants and products here, as I said, for redox reactions, we're not going to expect you to predict the products of the reaction, but we might give you the reactants and products and you have to add the coefficients. The first thing you'll want to do in a redox reaction is assign the oxidation numbers. So Cl- by itself has a -1 oxidation number, it's just equal to its charge. MnO4- is one we'll see in redox reactions a lot. Oxygen's -2 anytime it's in a compound. If you have 4 -2s, an overall charge of -1, the metal has to be +7. So manganese, this is as high as you go for manganese, has a +7 oxidation number. 7 plus 4 -2s is -1. That's the overall charge of the permanganate anion. We have H plus by itself, so the oxidation number is equal to the charge, which is +1. And then on the product side, we have ClO-. Remember that oxygen is more or less negative in chlorine, so it's going to be assigned as -2. And if oxygen is -2, and we have an overall charge of -1, that means the chlorine has to be +1. Okay? So +1 and -2, which adds up to give us a -1 total charge. Manganese +3 by itself has an oxidation number that's equivalent to its charge, which is +3. And then finally, H2O, like I said, we'll see this a lot in redox reactions, +1, -2. All right? So those are all the oxidation numbers, and there's really no shortcut around this. At the very least, you have to find the ones that are changing, but it's helpful to assign all of them to figure out which ones are in fact changing. So then what we have to do is we have to find the oxidation numbers that are changing between the reactants and the product side and determine the number of electrons that are lost or gained. Lost or gained for each species. And we really only care about the ones where the oxidation numbers are changing. Remember, the ones where the oxidation numbers stay the same, they're not gaining or losing electrons, but anytime the oxidation number changes between the left and the right side of the reaction, that means it's gaining or losing electrons. And we can figure out how many electrons are involved in that based on the difference in the oxidation number. So if the oxidation number changes by 2, that means it's 2 electrons. If the oxidation number changes by 3, that means there's 3 electrons, and so on. So if we look at what's going on here, we have the Cl- starts as -1, and then in the product side, chlorine is +1. So the oxidation number for chlorine is changing from -1 to +1, so that's a total of 2 electrons, a difference of 2. Now, if we really care what's happening here, the oxidation number is increasing, so that means it's losing electrons. It's getting more positive, so it's losing electrons. It doesn't really so much matter whether we put a negative sign on here in front, but we just want to know how many electrons are involved in that change, which is 2. And then we'll do it in a different color to keep it straight. So if we have the other one that's changing is manganese. That one starts at +7 and ends up at +3. And so if we look at manganese here, we draw a tie line between those two. Lagging again. That's a difference of 4 in the oxidation number, so that means manganese is gaining 4 electrons. Its oxidation number is decreasing by 4, which means it's a difference of 4 electrons. Okay? So always you're going to have one species losing electrons, one species gaining electrons. It doesn't so much matter if you keep those straight for the purposes of balancing, but we do need to know how many electrons that is. 2 electrons for this one, 4 electrons for this one. Now the next step is going to be to actually balance out the number of electrons. So what we have to do here is add coefficients to make sure that the number of electrons lost and gained is the same. Because in a redox reaction, we're not creating or destroying electrons. So however many electrons are lost from one species have to be gained by the other, and vice versa. So if we look at this reaction here, we saw that Cl minus going to ClO minus is a difference of 2 electrons. It's losing 2 electrons. MnO4 minus to Mn plus 3 is a difference of 4 electrons, but we need to have the number of electrons be the same each. So we have to add coefficients to make these balance. So if we put a coefficient of 2 in front of Cl minus and ClO minus, that means each of those is losing 2 electrons, happening twice for a total of 4. So if we double this, we'll now have 4 electrons lost, and the way we do that is we put a coefficient of 2 in front of each of those species. So 2 Cl minus is going to 2 ClO minuses. Each one involves losing 2 electrons, but it's happening twice now for a total of 4 electrons, such that the number of electrons lost is equal to the number of electrons gained by the other species. So you can't have an imbalance of electrons when you're doing this. All right, and then that also means because we've set these coefficients to 2, we don't want to change the coefficients on manganese anymore at all. So those want to be fixed at 1, so that still involves exactly 4 electrons. If we started putting coefficients on the manganese species now, we would now have more than 4 electrons involved, which would then unbalance the number of electrons again. So once you set the coefficients for the species that are being oxidized and reduced, you don't want to change those anymore. We stop, and we leave these as a 2 and a 1 and a 2 and a 1. But then the last step is to make sure everything else is balanced, and that we do by inspection, just by looking at what's left over. Okay, so we've already set these coefficients to 1, 2, 1, and now let's look at what we have left over. So we can balance hydrogen pretty easily. Well, let's balance oxygen first. Usually when you do this, we're going to balance oxygen first. So on the reactant side, we have 4 oxygens from permanganate. On the product side, we only have 2 oxygens for ClO minus. So if we put a 2 in front of water, that's going to balance the oxygen. So now we have a total of 4 oxygens on each side. And now by adding 2 waters to the product side, we have 4 hydrogens over here. We need to have 4 hydrogens over here. So we put a coefficient of 4 in front of H+. And then we could, at this point, verify that the number of atoms is the same on the left and the right, and that the charge is the same on the left and the right if you want to go that far and also determine that. So we add the coefficients last for the species that are not changing their oxidation numbers, and at that point it's just a matter of making sure that the number of atoms on each side is the same. So very often you'll see the same situation that we showed you here, which is that you'll use the number of waters to balance out oxygen on each side, and then you'll use the number of H pluses to balance out however many hydrogens you added from water. Okay, but you have to do those 2 last. Let's just see a few more examples of this. So let's look at this reaction here, which is dichromate and iodide and H+, making chromium 3 plus I2 and H2O. Now this is a situation here where we have to be a little bit careful when we have so we have 1 iodide on the reactant side and we have 2 on the product side. That's the only place that iodine shows up. So before we even start, we could determine that this I minus needs to have at least a coefficient of 2 in front of it. So sometimes it's helpful to do that because no matter what our final coefficients are, we have to have double whatever the coefficient is in I minus has to be twice the coefficient on I2. Because this only has 1 iodine and this has 2. So sometimes it's helpful, you can do this different ways, but I think it's helpful to put some of these coefficients in first. And then same story here for the chromium. So we have a Cr2O7, 2 minus, and a chromium 3 plus. This has 2 chromiums, this has 1. So no matter what our final coefficients are, we're going to have to double the coefficient on Cr3 plus. So I think it's helpful to put it in at the beginning sometimes in this situation where it's pretty obvious that we have to do that. Okay? So if we look at what's happening then with the oxidation numbers, Cr2O7 2 minus, we have minus 2 for oxygen. 7 minus 2s is a minus 14. We have to add plus 12 to get the overall to sum to minus 2. And so that means we have a plus 12 oxidation number for the 2 chromiums, which means each one is plus 6. Okay? So when you have two atoms you assume they have the same oxidation number. So the sum of the two oxidation numbers for chromium has to be plus 12 each one, and then it's going to be plus 6. You assume they're the same. I minus is pretty straightforward. That's an ion by itself, so it's minus 1. H plus is plus 1. Ion by itself, plus 3. I2 is an element by itself, so remember that those always have oxidation numbers of 0. And then our old friend H2O is plus 1 and minus 2. Okay, so those are all the oxidation numbers for every element in here. Assigning the oxidation numbers is pretty straightforward, but now we have to look at the number of electrons that are involved. So the ones that are changing are chromium, which is going from plus 6 to plus 3. But remember what's going on here. We know that dichromate has two chromiums, each is plus 6. So we have two chromium plus 6s, and they're forming two chromium plus 3s. So the number of electrons in total is going to be 6. Each one is changing by 3, but there's two of them, so it's a total of 6 electrons. So don't forget to account for that fact as well. We have 2 plus 6 is going to 2 plus 3s, so it's a total of 6 electrons. All right, so that's 6 electron process for the chromium. And then I minus is a similar story. We have 2 I minuses making I2. That's changing from minus 1 to 0, but that's the change for each iodine atom. But we have 2 of them. So we have 2 I minuses making I2. Each of those iodines is minus 1. Each of those is 0. So in total, that's going to be 2 electrons. Because each iodine is changing by 1, but there's 2 of them, so there's a total of 2 electrons. Some people don't add these coefficients in until later, but I think it's helpful to do that now, because no matter how we end up balancing this at the end, we have to have, again, double the coefficient on this one and double the coefficient on that one. So that's 6 electrons, that's 2 electrons. So if we want these to balance out, we have to change the coefficients. We have to triple the number of electrons that are involved here. So we triple those, which means then when we do that, we keep a coefficient of 1 on Cr2O72 minus. We have to triple the coefficient on I minus because that's a 2 electron process. We want to convert it into a 6 electron process, so we make that a 6. We have to balance H plus last, and then on the product side, we still have just a coefficient of 2 in front of chromium plus 3. We don't want to adjust that. So that's that's already 6 electrons. But then for I2, we saw that we had to triple the coefficients associated with the I minus I2 part of the reaction. So that's going to get a coefficient of 3. And then the last thing we do is H2O. So finally, to balance H2O and water by inspection, on the reactant side, we have 7 oxygens in our dichromate. So we have to put a 7 in front of water to balance that. By adding 7 waters, we now have 14 hydrogens over here. So we have to put a 14 in front of H plus that way. All right, and I can almost guarantee you, if you were to try to come up with these coefficients, just using the approach we did before, just by inspection, best guessing, and checking, it would take you a long time to get here, and maybe you never would. So by using the oxidation numbers, we can quickly identify the coefficients for the 4 species that are involved in the redox, and then we balance the rest at the very end. All right, let's just keep doing these. The more we do, the more familiar they'll become. All right, so this one here, we have potassium periodate plus ammonia, making potassium iodide, nitrogen, and water. All right, so this one asks us to balance and then determine the sum of the coefficients. So we have an ionic compound here. So that means the metal has the charge of the ion, which is plus 1. Potassium is a group 1 anion. O is going to be minus 2 whenever it's in a compound. So we have minus 2 for oxygen. We have plus 1. We have 4 minus 2s. And then to balance that out, we have to put a plus 7 on iodine. So that's the maximum oxidation number for iodine, which is a group 7, is plus 7. All right, NH3. Hydrogen is plus 1. We have 3 plus 1s. That means we have to have a minus 3 on nitrogen to balance the oxidation numbers for NH3. Potassium iodide is a very simple ionic compound, so it's going to be a plus 1 cation, minus 1 anion. N2 has an oxidation number of 0. It's just an element by itself. And then finally water, which we always see in many of these, +1, -2. So we've assigned all the oxidation numbers. We see a similar feature as last time, which is that we have only one nitrogen on the reactant side is NH3. The product has two nitrogens in N2. So again, right away we can know that we're going to have to double the coefficient of that. We can start with the 2 there, if that helps us. Okay, so now let's look at the number of electrons that are involved. So iodine is going from +7 to -1. So the difference is going to be 8 electrons. +7 to -1 is a difference of 8. And then nitrogen, we have 2 -3s going to 2 zeros. So each nitrogen is changing by 3 electrons. There's a total of 2 of them, so that gives us a sum of 6 electrons. So we need to balance these number of electrons out. We have 8 electrons for this conversion, 6 electrons for this one. How do we get those to equal the same number? What's the, I guess the least, what is it, I don't know the math term. The least common multiple? Is that right? I don't know. I'm terrible at math. But least common multiple of 8 and 6, we have to find what that is. That's going to be what? So it's not 16, it's not 12, it's going to be 24, right? So we can, if we triple this one and we quadruple this one, they're both going to be 24 electron processes, and that's the smallest number of electrons we can use to balance this out. So 8 electrons for this one, 6 for this one, we triple it to get 24, we quadruple that to get 24 also. So that means we need to then adjust the coefficients accordingly. So the coefficients for KiO4 and Ki need to be tripled, so we're going to have 3 KiO4. The coefficients for the nitrogen-containing species have to be multiplied by 4. So we started with a 2 in front of NH3, so that has to be quadrupled to give us 8. And then on the product side, we have to triple the coefficient for Ki. We have to quadruple the coefficient for N2. And then finally we have water, which we have to balance last. So if we look at oxygen here, we have 3 times 4, we have 12 oxygens on the reactant side, so we have to have 12 waters on the product side to balance that out. 12 H2O. And we can also check then the hydrogen's balance at this point as well, 24 on each side. All right, so again, some pretty big coefficients here, not something that would be very easy to come up with by inspection. So the question then asks for the sum of the coefficients. So it's going to be 3 plus 8 plus 3 plus 4 plus 12. Right, and that's going to be 30. So very often, again, in homework questions and test questions, we'll have you balance the reaction and then ask you, what's the sum of the coefficients? That's our way of checking if you did it right. And so if you add all these up, you get 30. All right, so like I said, for redox reactions, you often have large coefficients. Now I want to do this last one here because it introduces a slightly new feature. So we have zinc plus nitric acid making zinc nitrate, NO, and water. So quickly to go through this one, the oxidation numbers, we have a 0 for zinc, it's an element by itself, +1, -2, and +5 for nitric acid. I'm going to do these quickly because we're running out of time, and I know you guys are all dying to start your break. We have +2 for zinc nitrates, it's an ionic compound with a +2 charge. We have +5 and -2 for oxygen to balance that. NO is +2 -2, my bad. Trying to work too fast here. So -2 for oxygen, +2 for nitrogen to balance that. Water again, see it all the time. Okay, so if we look at what's changing its oxidation number, zinc is going from 0 to +2, so that's 2 electrons. This nitrogen +5 to +2, that's 3 electrons. However, the issue here is that we also see that on the product side we have some nitrogen that's still at +5. So not all of the nitrogen is changing its oxidation number. You have this one going from +5 to +2, but we also have some nitrogen that's still in the form of nitrate and still has a +5 oxidation number. So how do we deal with that? If this is the case where some nitrogen does not change its oxidation number, a convenient way to handle this is to separate it out into 2 portions. So one portion of the HNO3 we're going to balance out using the oxidation number approach based on how many electrons it's losing or gaining. the other portion we're going to balance by inspection at the end to make sure that everything is totally balanced. So we have zinc, we have HNO3, we have another HNO3, and that forms zinc nitrate plus NO plus H2O. And then, as I said, we have zinc going from 0 to +2, that's 2 electrons. This nitrogen is going from +5 to +2, so that's 3 electrons. So we can then balance these 4 species just by making sure the number of electrons are balanced. So we have to then triple this to make it 6 electrons, double that to make it 6 electrons. So then what we end up with is we triple the coefficient on zinc, we double the coefficient on the first HNO3. We still have to balance the second HNO3. And then we get zinc nitrate. We have to triple that coefficient because it was part of that process. We have to then double the coefficient on NO. It's part of this 3 electron process. We put 2 NOs and then water. To balance the rest by inspection, we have still, this should be nitrate taken twice. We still have 6 more nitrates over here, 6 more nitrogens over here that are part of zinc nitrate. So we put a 6 in front of that to balance out the rest of the nitrogen that's not changing its oxidation number. And then for water, we have to put a coefficient of 4 to balance out the oxygens. So basically these 2 nitric acids are each losing 2 oxygens to make NO, so we have 4 more oxygens we have to put over here. So then when we simplify this out, we get 3 zincs plus 8 HNO3. We add the 2 coefficients, 2 and 6, and combine them, and that's going to form 3 zinc nitrates, 2 NOs, and 4 waters. All right. So again, if you have some atoms that are where some of them are changing their oxidation number, some of them aren't, it's helpful to balance in 2 parts. Yes. Yeah, there is no zinc nitrate on the reactant side. The reactant side is just HNO3. Right, I did that on purpose because part of it we balanced by looking at the number of electrons it was losing, and then the other part we balanced at the end by inspection. So whenever you have that situation where something is both involved in the redox reaction and also not involved in the redox reaction, so it has some that are changing, some that aren't. So some of the nitrogen goes to +2, some of it stays at +5, so we balance it in 2 parts. All right, we're out of time. I guess if you're going to the rodeo tonight, I'll see you there. If not, I'll see you after spring break.